morning, everyone. Good morning. Welcome to the second day of our workshop. Thank you for coming. Thank you for being here. Just a quick announcement. You have to cast your votes for the best paper. It would be better to do by lunchtime if you want. People are asking me how to vote because the ballot is not so that clear. Let's do the following. Select 3 of the best posters that you like and put like 1, 2, 3, and then vote for 3 and saying which one is the best one, the second and the third, and then we will compute the votes afterward. All right. For people that are not here, if you see someone that arrives later or etc., just tell them about this arrangement. All right. So you can vote for 3 of the best posters. So we can compute the final score. All right, so just a quick reminder that we are transmitting this event on YouTube, right? So if somebody that is not here wants to see the event, there is a link in the channel, ICMC channel, right? It's a pleasure to introduce here my friend, José Alberto. Thank you for coming, João. João is professor at the Institute of ITA, Instituto Tecnológico de Aeronáutica. I don't know how to translate that. And yeah, he has a strong background in aerodynamics and simulations, large scale simulations in aerodynamics. And this is the topic that he's gonna talk about today. And yeah, João, it's together in the SEMI since the beginning, since the first, actually before SEMI with the way before with the projects with Embraer, with FAPESP, and now with SEMI. So it's a pleasure to have you here, João. João was also president of CNPq, so it's a very, very important guy. João, thank you for coming, and the floor is yours. Thank you.
Thank you, Fabrício. Yeah, thank God CNPq time is over, right? CNPq time is over. Anyway, so good morning, everybody. It's a pleasure to be here. I hate to use those things, and I usually don't need to use that. I have a loud enough voice, but apparently they are transmitting, so I have to use it. Again, it's a pleasure to be here, okay? I had to be here celebrating Poti's birthday. I mean, Poti is a very good friend, old friend probably, okay? We are both old, okay? Anyway, so like I said, it's a pleasure to be here. So the title of my talk this morning is a study on the use of nonlinear eddy viscosity models in aerodynamic applications. And I mentioned there a PhD student that are working on this in our group, okay? All right, so this is what I intend to do. So Fabrício can look at where I am and see if I'm too late or not, but hopefully I'll be able to do in 40 minutes, okay? All right, so I guess the first important thing is why we are doing this work, okay? So, you know, I'm sure all of you are aware that many aeronautical applications really depend on reliable prediction of turbulence and actually, in some cases, reliable prediction of transition, okay? And of course, I mean, some colleagues, including ourselves, okay, are using LES or wall model LES to investigate flows in which usual runs turbulence models are known to fail. You know, in aeronautics, we're talking about pretty high Reynolds numbers, okay, 10 to the 6, 10 to the 7, 10 to the 8. So if you think about it, I mean, you know, if we use, you know, LES at a wall, okay, the mesh refinements is almost like a DNS, right? So that's very expensive, and that's why some people are using wall model LES for those flows. It was quite a bit of success, okay? And again, especially with things that have a lot of separation and things like that, okay? But if you look at the aeronautic industry, okay, the workhorse, okay, for industry applications, is still, I mean, the runs formulation, okay, and especially, you know, runs formulation with the linear eddy viscosity model, okay. So besides being involved with semi-I and all the work with people over here, okay, we are also involved in another FAPESP project. It's called an Engineering Research Center for Aero Mobility of the Future. And this is something that has to do with ITA, Embraer, and other universities. USP, I think it's USP São Paulo, right? But Unicamp and so on. So again, working very close with Embraer, and it becomes evident, okay, that they're still using runs for their calculations, okay? So, I mean, in some sense, then, there is interest, okay, in looking into possibilities to extend the ability of a runs formulation, of runs models, for treating relevant aeronautical flows. And that's why we're doing what we're doing, okay? So, I mean, I guess if I had to summarize in a single sentence, the motivation for what we are doing is that we want to provide continuous improvement in the capability of treating turbulent flow simulations using the runs equations, okay? So I guess I already mentioned most of that, but essentially, although people do use those simulations to do aeroelastic things, okay, but most of the work, at least in Embraer, they use it for aerodynamic simulations. Those are compressible flows, viscous flows, and this is the day-to-day stuff that they do over there, okay? So, and if you look at it, I mean, it'll probably remain like that for a few years. So there are reasons for looking into ways, let's say, of trying to improve our run solutions, okay? And of course, one way of doing this is to do a better modeling of the Reynolds stress tensor, okay? So of course, I mean, that essentially means trying to use more advanced turbulence models. Of course, I mean, like I mentioned, like I already said, right? I mean, most of the work in industry is done with linear eddy viscosity models. Of course, I mean, the other side of it, okay, is to use, Reynolds stress models, but this is very expensive. So in some sense, what we are betting is that, there is something in between, okay, what probably could be an alternative for that, which is, again, like I said, the use of nonlinear eddy viscosity models. And in particular, we are looking at explicit algebraic Reynolds stress models, okay? So then the objective of this work that I'll be describing to you today, or at least the long-term objective, we are not there yet, of course, but I mean, the long-term objective is to test a few nonlinear turbulence models in typical aeronautical applications, again, trying to incorporate an isotropy of the Reynolds stress in the Reynolds stress calculations, but at the same time, keep the structure of your computational code essentially pretty much as it is for a linear turbulence model, okay? That makes it easier to implement, and hopefully, and I'll mention this at least at the end of my talk, that there's a low increase in computational cost. And again, as I said, we are looking at explicitly algebraic Reynolds stress models, or EARSMs. All right, so I'll try to show as few equations as possible, okay? So I'll do a little bit of hand waving over here, but I have equations there. If anybody really wants to see the equations, ask me at the end, okay? So essentially, I mean, with linear eddy viscosity models, they are based on the Businevsky hypothesis. And essentially, you're saying that there is a linear relation between your Reynolds stresses and the deformation, right? The deformation of the velocity field, okay? Or the Sij is the symmetric part of the velocity gradient tensor, okay? So again, it represents the deformation of the fluid flow, okay? All right, so this is what linear models does. So the idea was nonlinear models, okay, and especially with explicit algebraic Reynolds stress models, is to add to that equation some nonlinearities, maybe included here a term that has to do, again, S is the symmetric part of the velocity gradient tensor, and omega is the anti-symmetric part of it. And hopefully, from those terms there, you could also maybe increment the way we compute the eddy viscosity. Okay, that's the basic idea. All right, so how do ERSM works? ERSMs work. Okay, so essentially you have you perform an algebraic and explicit expansion of the Reynolds stress tensor. Typically, this is like a polynomial in S and omega, and that constitutes your constitutive algebraic model, and you couple that with some eddy viscosity turbulence model. Okay, you couple that together with information that come from this constitutive algebraic model. So essentially, from that expansion, you determine the coefficients on that, and you compute coefficients which are going to increment your mu t, and you compute an anisotropy tensor. Okay, and then the tau ij, as I showed on the previous slide, it has some nonlinear information in it. Okay. Again, this is what I meant before, and again now you have this guy, which also has information from the expansion of the Reynolds stress tensor, the algebraic expansion of the Reynolds stress tensor, and then you incorporate some anisotropy over there. We started working with this model. It's called the NL-BSL, and NL is nonlinear, stands for nonlinear BSL, because it's essentially constructed on top of the well-known SST model, but not exactly the SST version of the model, what Mentor calls the BSL, the baseline model, okay, which is essentially exactly the same equations of the SST model, except that the definition of the eddy viscosity is different. Okay, so essentially, this is a model that was created by Halston in 2005, using a constitutive model created by Wallet and Johansson in 2000. Okay, and the coefficients of the model that Halston calibrated were for high lift conditions. Okay, and we started working on that, and then we made some small modifications to it. Like I said, I have the equations if you guys want to see it later. Okay, but I rather not show them right now. But essentially, we changed the way we define the production term of the omega equation. Okay. So, and we thought that was a very simple modification, and actually we get fairly different results, at least for some cases, with this other version of the model. Okay, and especially, I mean, for compressible flows, for flows with shock waves and things like that, it seems to give better results. Okay, like I said, I mean, if you go all of those K omega or K epsilon models, if you look at the production term of the omega equation, of the epsilon equation, and essentially people get the production term that you have from the K equation, you divide by K and multiply by omega. That's essentially what you do. Okay, but I mean, if you look at a K omega model, the velocity scale, the turbulent velocity scale is square root of K, and the length scale is the square root of K divided by omega. So essentially, if you have K over omega, that's proportional to nu t. So this is essentially what we did. We replaced K divided by omega in the production equation, in the production term for the omega equation by nu t. And, you know, a lot of different things happen anyway. But I'll show you. So this is what sort of created this NL-BSL V2 for version 2, obviously. Okay. All right. So just one slide about the numerics of it. I mean, our code is a self-centered, standard finite volume code. Okay, it's standard, I mean second order, nothing really fancy there. Okay, for general unstructured grids, convective fluxes uses the row scheme, a muscle-like reconstruction to get properties at cell faces in order to get second order. We use what we call the Wang limiter, which is essentially a modification, the well-known Vikata-Krishnan limiter. Some things are done a little bit differently, I mean. By the way, I don't know if everybody's aware, but Professor Rowe passed away just 9 days ago, was on Sunday, the April 26th. Okay, so it's, anyway, so, but we're using the Rowe method, okay? All right, so for the viscous fluxes, you need, besides the properties at the cell interfaces, you also need gradients at the cell interfaces, okay? So essentially, what we do is that we compute cell average gradients using a weighted Green-Gauss kind of approach. And from that, we constructed, I mean, there's more detail to it, but again, I'm trying to avoid a lot of equations here, but there's more, we construct actually gradients at the cell interface, okay? It's an implicit time march, and you use GMRS for solving linear system, okay? All right, so how am I doing here? I'm doing good. Okay, so I'll present three cases to you, okay? The first one is the typical, sanity check, okay? If you cannot do a flat plate flow, but go home, right? So this is a zero gradient flat plate flow, low subsonic, Mach number 0.2, Reynolds number 5 million, okay? We are using 3 meshes, and the comparison are with results that are available at the TMR. TMR is the Turbulence Modeling Resource, okay? Is a site hosted at NASA Langley Research Center where people have a lot of information about that can use to implement and to test turbulence models. So the results at the TMR were computed using the CFL 3D code, which is also a very old NASA code, and the comparison is done with a different version of the SST model. Okay, well, I'm sure you guys are pretty aware of that, but both the Spolar-Tomaras model, which is well-known model for aerodynamic applications, and the SST model have several versions. So I mean, so it's saying that you're using Spolar-Tomaras or SST is like going to a German bar and asking for a beer. Okay, I mean, the waiter's going to be mad at you because you got to say what kind of beer. So you got to say what kind of SST, what kind of SA, right? So this is here the definition. Again, the details are on the TMR website, okay? All right, so we're looking here, at mu-T contours, okay, the eddy viscosity contours, computed with the Helston model, okay, for a coarse grid, for a medium grid, and then we have also results for a fine grid, okay? And if I go back a little bit, I mean, if you see, I mean, it's all pretty consistent, okay? I mean, they're getting better to refine the mesh. And of course, I mean, if you look at the results that come from the SST model, they obviously not exactly equal, right? Because it's a different model, it's a different numerics in the code too. But anyway, so at least it's telling us that, well, it seems that things are okay, right? A more detailed comparison here in terms of the velocity profile in the boundary layer, okay? Our results are the blue curves, okay? So essentially it means that we are getting the right results in the viscous sublayer, also getting the correct results in the log part of the boundary layer. And by the way, I mean, the plate has a total length of 2L. L is the reference length. So the light blue curve is sort of halfway along the plate, and this other dark blue curve here is way towards the downstream boundary of the simulation. Okay, so again, not much there. Okay, but again, sanity check done. Okay, all right. So the second case is probably more interesting. This is a flow in over a bump in a channel. Okay, it's still low Mach number, pretty high, 5 million Reynolds number. We still look at this as a verification test case, okay? Again, we use 2 meshes. The reference results, again, are on the TMR, and they were computed with another NASA code called Fun3D. And you see we're comparing our results to several different turbulence models, okay? I'll try to sort of convey to you what the simulation looks like. So you have a channel, okay, flow comes in from the left, goes out on the right. The bump is on the bottom here, okay, but the whole bottom is not a wall, okay. There's only a wall in a portion of the bottom here where the bump is, okay. The rest, I mean, you have symmetry boundary conditions here, symmetry boundary conditions in the back, symmetry boundary conditions in the top, and also down here upstream of the bump and downstream of the bump are also symmetry boundary conditions, okay? And of course, I mean, the inflow conditions here, outflow conditions there. Remember, this is a low Mach number case, okay? The bump, and it's a bit exaggerated here, okay, in the vertical direction, but the bump looks something like that, okay? This is a sinusoidal bump, okay? This is sort of, the bump is not straight, okay? It's sort of, yeah, otherwise it would not be that interesting. Anyway, so this thing here is the bump configuration over here, okay? The axis along the direction of the flow, y is span-wise, and z is vertical. Vertical from the bottom of the channel, okay? So essentially what we saw there is the bump distribution over there, which is symmetric with this guy here, and then the bump goes sort of like that, okay? And all the dimensions are there anyway. So, and again, this is sort of a view of the mesh, okay, for this flow. All right, so I'll show some of those visualizations for the NLBSL model, and some of them from the NLBSL V2 model, okay? Here we are looking at mu t, right, or at the eddy viscosity, and x equals 0.3 is where the wall is just starting at the center line of the channel, but there is already a bump here as you move outwards to those two symmetry planes, this way and that way. So, and that's why you're seeing, quite a bit of mu t being created here, almost nothing there, just because the wall is just starting at x equals 0.3 at the center line, okay? So again, we're looking at the results that we computed with NLBSL solver, or NLBSL model here, and those are results from the TMR with this SST-VM model, okay? Okay, this is mu t, this is k, this is the turbulent kinetic energy, and again, I mean, obviously the contours are not exactly the same, okay, but you see that there is some pretty good correlation, and this is omega, right? This is the rate of turbulence dissipation, right? I mean, again, the model is based on SST, so I mean, the second equation is for omega, right? Again, the results with NLBSL and the results with SST from the TMR. Again, still the same position, right? I mean, there's some, not exactly identical, but it's pretty good correlation, right? And now we're looking at another axial position, right? And x equals 1.2 is just a bit downstream of the highest part of the bump at the center line, okay? And again, I mean, the comparison now is done with the NLBSL V2, okay? But again, the results there are results for both models for all locations, obviously, okay? Again, looking at mu t over here, as you see, again, not identical, but things do make sense. This is again for K, for turbulent kinetic energy, and this here for omega. I mean, dimensionless omega, of course, right? So, okay, so again, my point is, with all of those things are that obviously the results are different, of course, right? But they do make sense, okay? The things seem to be computing the same flow at least, okay? Here we're looking at the CL coefficient, right? How am I doing here? I'm okay. The CL coefficient at the bump, okay? The red and blue curves are our computation. The red is with the NLBSL model, and blue is NLBSL V2 model, okay? And we are comparing here with, again, the solutions at the TMR with SST and with the Spolato-Maras model. The H is like a representative mesh size, is 1 over the number of cells to 1/3. So mesh refinement happens this way. So the more to the left, the more refined the mesh, okay? So essentially, we're asking here how the lift coefficient behaves as we refine the mesh, okay? And obviously, we can look at there. We are not mesh convergent yet, of course, but there is a finer mesh for this case, but it isn't actually available anymore in the sense that apparently the mesh was too big and people took it out of the website. But anyway, so this is the comparison with these two models, which again are linear eddy viscosity models, right? Compared with the explicit algebraic Reynolds stress models there. And now we are comparing that with two other models, with a Reynolds stress model over here, okay? Again, those are results that are available at the TMR, okay? And a nonlinear version of the SA model is RC stands for rotation correction, and QCR stands for quadratic. Oh my God, what's the word that escaped me? Anyway, it's a quadratic law there, okay? Anyway, so again, still look at CL, obviously not mesh convergent, but the behavior looks pretty good. And actually, for the NL-BSL, you see this appears to be, converging to some with regard to the mesh, right? The same sort of comparison. Now, looking at the drag coefficient, okay? Again, it's the same thing as before. Red and blue were our results compared with SA and the SST, okay? As we refine the mesh, of course, I mean, the drag correlation becomes better, I guess, right? And then with the other two models, the nonlinear SA and the RSM model. Okay. People sometimes don't like to look at residuals, but I think it's important to look at residuals. Again, those are for the finest mesh in the bump, okay, in the bump calculations. Here are the residuals. I mean, this is L infinite norm of the residuals, okay? For the five equations, right? For the 5 conserved variables here, and for the turbulence model variables over there. Not really great, some spikes here and there. And again, this is with the Helston model, okay? Not too different, but a little bit better behavior with the version 2 of the model, right? And again, I mean, those are the 5 residuals for the conserved variables and the turbulence model residuals. All right, so my last example, or my last test case, okay, is a transonic flow, OAT-15A airfoil. This is really, again, like I said, it's transonic flow, so Mach number is 0.724, Reynolds number is 3 million, and the angle of attack is 1.15 degrees, okay? As before, 3 meshes, and now we are comparing here with SST calculations, a different version of the SST is the one that we have implemented in our code, okay? And also comparison with experimental results. All right, so those are the 3 meshes, like coarse, medium, and fine. The external boundary is at 120 chords from the airfoil, okay? All right, so those are pressure coefficient distributions on the airfoil in the finest mesh, okay? Purple is our SST calculation. The light blue is the Helston model, and the dark blue is the NL-BSL-V2 model, okay? And the open symbols are the experimental data. Well, I guess the best way to put this is that if you look at the lower surface of the airfoil, it's pretty good comparison. Throughout most of the upper surface also, there's a very good comparison, except over here, and at the shock wave, okay? So if you sort of do a zoom in this area here, this is what I'm showing there. What you see is that the SST calculation puts the shock quite a bit aft of the actual position, okay? Doing the calculation with the Helston model, it improves the shock position, but it's still quite a bit aft. And with the version 2 of the model, it does quite a bit of better job, okay, in positioning the shock there, okay? If we look at lift and drag coefficients, I mean, the integrated coefficient for that. What you see is that for lift coefficient at least, and by the way, this is percentage error with respect to the experimental data, okay? So there's not a lot of improvement in the error as you refine the mesh in this case, okay? But you do see a much better lift or much less error in the lift with an LBSL2 model, an LBSL V2 model. With the drag, it's a bit more complicated. Of course, the error in the drag is larger, and in some sense, I'm happy with that. I mean, if you get the drag right and you get the lift wrong, maybe your computation, there's something wrong there, because it's much harder to compute drag than it is to compute lift. Anyway, so for the drag, you see that there is some improvement for all models with the grid refinement. Okay, for the lift, you don't see much difference. All right, so we have a better result, okay, with the new version of the model. The question is, why do I have a better result with the new version of the model? And I don't have an answer yet, okay, but we're looking at it, okay? So we look at several things, and one of the things that we look at, you know, some contours, in this case of turbulent kinetic energy, okay? Try to look here in the, close to the leading edge, where the shock is, and close to the trailing edge, okay? And look, a lot of different other things too, but anyway, so I'll be showing only the results for the K contours at the shock position here, okay? So those vertical lines are essentially where the shock is located, okay? Well, the numerical shock is not in a single cell, right? So it is distributed. So what was those broken lines, what they are showing is where the shock is, okay? So this is the result for the SST. This is for Helston's model. You see, I mean, the shock position moved a bit forward, okay? And I guess what I can say is that, you know, the highest, you know, production of K in some sense happens after the shock for the SST. Over here, there's much more K, all right, at the foot of the shock, but it seems that this region sort of moved forward a little bit. And if we compare again now with the NLBSL, of course, I mean, the shock moved forward even more, right? But again, I mean, is not as much K in there, okay? But it sort of has the same location with respect to the shock, or the region of maximum K has the same location with respect to the shock that we had in the NLBSL model, okay? All right, again, looking at residuals. Again, this is for the finest mesh with the Helston model. It's a pretty good convergence, okay, and for the conserved variables, and well, not so much for the turbulent variables over there, okay. With the NLBSL V2, well, seems a little bit of oscillations here, but again, quite a reasonable drop in the residuals, okay? Well, the turbulence model variables are really complicated to get them to drop anyway. Okay, so just then a summary, okay? We look at our case 1 and case 2 essentially as verification types of cases, looking whether we had implemented things correctly, okay? Case 3, we start to look, you know, try to do some sort of validation and see how this compares with experimental data. And we are looking at different airfoils and all different, even 3D calculations with, you know, on-Orion, 6 wings and things like that. And this is what we are doing now, I guess the most important thing is, okay, so what is the point, right? I mean, what have we learned from all of this exercise, okay? And I guess the first point is that, like I wrote in there, the overall experience with the explicit algebraic range stress models seems to indicate that they really do not add any additional mesh requirements, so we don't have to make a finer mesh for them to work or anything like that, or even additional complexity to resolve the flow. So the number of iterations to get a converged solution, or I mean the behavior of the residual is not really worse than it was for the underlying SST model or BSL model, I guess, right? I didn't say much about cost, okay, but cost was an important part of that. And what you see is that the cost of using the EARSMs is just 20 to 22% higher than the cost of using a linear model like SST, okay? So again, 20% is not a whole lot to pay, okay, to maybe have more physics in the solution, okay? An apparently very simple change in the ERSM actually yield quite different results, okay? And like I said, I mean, what we're doing right now is trying to understand, okay, what parts or which terms in the model are primarily responsible for such effects, okay? We're trying to understand which parts of the model are causing those effects, okay? And of course, I mean, I mentioned transition in the beginning, okay? There are plans to couple this NLBSLV2 model with a transition model, okay? Like I said, again, there are quite a few applications in which the transition location is very important in order for you to get your drag right and all those things that people are looking at in aerodynamics, okay? And let's see, I guess, yeah, this is what I had, okay? Thank you so much for your attention. I'll be glad to try to answer any questions that you have. Thank you.
Thank you, João, for your very nice presentation. We have already
a customer there. I have a customer there already. Okay.
Customer.
Excellent talk as usual. Can you please put the slides on the convergence?
Okay.
And you show too that one.
This one?
Yeah. For instance, why the new version, the version 2, doesn't have any spikes as is shown in, because this is important. This is smoother convergence. You can have the computations, much less iterations. You see,
yeah.
This is,
I need to use this, okay? It's a great question, okay? And I wish I knew the answer, okay? But I can tell you this, we observed that, okay? In this case, actually, if you look at the residue curves, okay, for the new version of the model, they're a little bit worse than but not a big deal. But if you go back for the other case, right? This is actually seems to be representative of what we saw, okay? I cannot tell you why, because I don't know. But, and this is what we are trying to figure out right now. I mean, what is happening? But actually, the new version of the model seems to converge better. I mean, this behavior here, like we saw for the 3D bump, okay, in which we see some spikes here on the Helston model, and we don't see much stuff. I mean, in the new version of the model, seems to be more representative of what we have seen. And actually, this is even better than I didn't show here the SST residuals, okay, but they have spikes too, okay. So it's
yeah.
It's like interesting, okay.
Yeah,
that's all I can say.
Freezing delimiters, for instance. You know,
I mean, it's the same limiter for all of them, okay? So all the rest of the numericals is the same, okay? The only difference is, because, I mean, we have SST, we have SA implemented in the code, so we can run those cases with all of those models. And actually, this guy here seems to behave better, okay, than even the SST, which is a linear model, or the older version of the... And actually, I mean, since I have a couple of minutes, let me show you guys the difference, okay? Yeah. I had this as, you know, extra slides or backup slides, okay? So
a real pro.
Okay, so these are the equations for the Helston model, okay? The K equation, the omega equation, right? And like I said, I mean, with all K omega, K epsilon models, okay, what you do in the production term for the omega equation, you get the production term for the K equation. In this case, it's a K omega model, right? So you multiply by omega and divide by K. Okay, that's the obvious thing, okay? Right, so like I said, the problem is, or what we sort of realized was that the turbulent velocity scale is square root of K. The turbulent length scale is square root of K over omega. So K over omega is proportional to nu T. So that's what we did, okay? This is the only change is this one, okay? This is the omega equation for the original Helston model. This is the omega equation for the NLBSLV2 model, okay? So, I mean, of course, I mean, there's a Reynolds number there and so on, but essentially, we got K over omega, which is here in the denominator, and replace that by nu T, okay? Of course, I mean, it seems to be a simple change. It's not that simple, because, of course, nu T has all of this, you know, all of this stuff here, that's C mu effective coefficient and so on and so forth. So that there is a lot of stuff that is in there. So it's not a linear thing in some sense, okay? But it seems to be a very simple change and seems to improve the results. Now we have to figure out why. Yes, please.
Oh, thank you for the talk. What transitional model are you considering to use?
We haven't really decided yet, but we have more experience with the Langevin-Mentor model, okay? Because we work with that already. So we implemented the Langevin-Mentor model together with the SST in the code, okay? So we will certainly start with the Langevin-Mentor model. Whether we'll stay with that, I cannot tell you, but because I don't know, right? But we'll start with the Gamma Reynolds Theta model, the Langevin-Mentor model, okay?
We have one more question here. Livia.
Thank you, Professor. Very interesting. I'm curious if for the first two cases you did some check that you had a LES or DNS reference to know if the changes on the model are going in the right direction. That's my first question. If there is some simple cases that you have that kind of data?
No, I don't think we have that information, okay? We have information on several different other runs models, but I don't believe, I don't remember exactly, but I don't believe there is information there for the DNS or LES solutions for those test cases, okay?
Because those changes in the drag and lift coefficients, they have a tendency of being higher, right? Is that do you expect that to be in the
What do you mean?
right direction?
Over here, let's see, what are we looking at? Looking at this guy here, for instance, right?
I think.
Yeah, we are getting a higher drag. You're right, okay? Whether that's the correct solution or not, I don't know, okay? And of course, I mean, in some sense, what I am, or what I was concerned when we're doing that, is whether we'll be eventually converging to the correct drag, okay? And at least what I have seen is that different models behave in different ways. Sometimes if the mesh is too coarse, it's a very, very large error. But as you refine the mesh, you converge to the right solution, right? So I never look at it the way you're looking. So but I don't think there is this DNS or LES data over there, okay? For those configurations.
And a second question. So no, that's fine. I'll ask you later. Thank you.
Well, thank you. Am I done?
One last question here from.
Okay, good.
A guy that's hidden in the back.
A nice talk, John. Thank you for your discussion in terms of nonlinear models. And I asked you for Leandro about, maybe it's a naive question. I don't know, I am not a run guy. But what is the strategy to select the nonlinear terms? Because as I understood, you improve the runs using nonlinear models or nonlinear terms. Could you just say something about this, just to have an idea?
I got it, okay.
Thank you.
You see, what you do is that you represent the Reynolds stresses by a sort of a polynomial expansion, if you let me talk it this way, okay, in which the terms are, let me go back to the equation and then it'll be easier to explain. One more. Okay, so essentially it's like a polynomial, an algebraic polynomial expansion, okay, where you use Sij and omega ij, okay, so it's a polynomial in Sij and omega ij. There are some invariants of the Reynolds stresses. There are sort of coefficients for those polynomials or that are in there in those polynomials. And you also have coefficients that you have to calculate a value for them, okay? So for instance, let's see, I had I don't know what it is anymore, but, well, I'll probably won't be able to find, but there is an expression there that appears beta whatever, beta n, and this is one of the coefficients that has to be calculated in terms of those invariants of the Reynolds stresses, okay? And there are some of the invariants, they appear in some of those terms in there. So essentially that's what you do, okay? You represent the Reynolds stresses or the anisotropy, if you will, okay, in terms of this expansion. But it is an algebraic expansion, okay? And then you're not solving an additional differential equation. So, and that's why the cost is essentially the same cost as the cost of the SST model. So it is built on top of the equations for the SST, but those guys there, the mu t, the C mu guy, and so on, they are computed based on terms of this expansion of the Reynolds stresses, okay? And also the anisotropy tensor, okay? It's algebraically calculated based on this expansion. It's interesting because, you know, you have to look at a Reynolds stress model, and after you understand the Reynolds stress model, then you can come back and understand how the nonlinear model is formulated, okay? But it is a very ingenious thing, okay? It works very well, actually, as we saw.
All right, satisfied? Okay. Okay, let's thank João again.
Thank you, guys. Thank you very much for the attention.
Thank you, João. Very good discussion. All right, we now go for the last coffee break before the best poster election. All right, so don't forget to cast your votes. Remember to put like 1, 2, 3, the best one, second best, and third best. All right, thank you so much. Let's go for coffee. Obrigado. Vamos lá. Welcome everybody. Good morning again. Let's start our second session this morning. It's a pleasure to me to introduce Norberto Mangiavacchi. Norberto has a long history of collaboration with us. Actually, he worked here. He was in this very group when I started my master's degree, my PhD, and he was my supervisor in both of them. Thank you, Norberto, for that. And Norberto collaborated a lot with us also after going to Rio, and he had a big project there with Furnas and Gesar. He is head of the Gesar group there, so it's a very, very good group and very good installations in the State University of Rio de Janeiro. And it's a great pleasure to have you here. Thank you for coming. Norberto is going to talk about numerical modeling of magnetic particle recovery in laminar flows. So Norberto, thanks again. Floor is yours.
Well, thank you, Fabrício, for the invitation, the opportunity to be here with friends. You know, it's a great pleasure to be here. And so I'm going to, as Fabrício said, this is a work that Igor Ares is developing in his master with me, and also with the collaboration of Raquel Lucena from State University of Rio de Janeiro, Hyun Ho Shin from the Universidad Nacional de Asunción, Paraguay, and Luis Portela from TU Delft. So maybe here. So first of all, I think most important of the talk, I really need to thank Poti, because as Fabrício said, I started here in 1998, and I had an excellent stay here. And it was, I think, Poti opened the doors for me to this group. At the time, it was the LCAD, which was really a place where I grew a lot with the collaborations, also with many people that are here now, and also others that are not here. But so it's a great pleasure. And I thank very much Poti for the opportunity. So, so this is the most important part of the talk. Now I move to the rest. So, okay. So I've been working lately on for some time with particles in fluids, some part bubbles, drops, and then I'm starting to move to solid particles that have some interesting applications. And lately, on a FINEP project, we were working with the water treatment. So the idea of using magnetic particles is not new, but is still in development. So the idea is to put particles in the flow that have magnetic properties. And with this, you can either steer the flow using a variable magnetic field, or you could use magnetic field to separate particles. So you can manage the particles using the magnetic field. So these magnetic particles range from nanometers to micrometers. So usually they are employed iron oxide to have magnetic properties, and it's because also it's cheap and it's not environmentally problematic. So, and if you don't want to have very small particles, but still have good magnetic properties, it's been developed a technology using hydrogel microbeds that still have very strong magnetic properties, but they are much larger and still have very good absorption capacity. So changing the coating on the particles, you can change the functionality of the particles. So you can use them to remove many kinds of pollutants. For instance, you can even use it to remove nanoplastics. So, but you can also use it to remove, for instance, antibiotics and hormones from water. So they are very good for environmental cleaning. So the challenge is to simulate the particles in the flow subject to this magnetic field. So I'm going to talk about these modeling strategies, starting from the very simple one, but that which gives already a good feeling, good idea of how the particles behave. And then we move to a more general setting to be able to study more complex situations. But in general, we consider that we are dealing with a Newtonian fluid, and the particles are either monodisperse or polydisperse. Most of the time, we'll be dealing with monodisperse because we have control usually on the process of generating these particles. So they are essentially, they have a size which is quite controlled. We also are interested in applications where the amount of particles that you have is relatively small. So you have dilute to moderate concentrations. And we'll talk about one- and two-way coupling, meaning that in one-way coupling, we only consider the effect of the fluid on the particle. We don't go the other way, which is the two-way coupling, when you consider the effect of the particle on the flow. So we look at the two approaches. So one-way coupling is usually applies very well for very low particle concentration. So when you have very few particles, you can neglect the interaction of the particles with the flow. So the flow velocity is given just by the Navier-Stokes equations on the domain with the boundary conditions without the effect of the particles. And the particles can be either simulated or modeled as individual particles or as a field. So, and this is what we are going to show. I think this is not good. So I go by hand. So as I say, Navier-Stokes, and for the particles in one-way coupling, we have to use the momentum balance to compute trajectories and do the mass conservation. Acho que não. Tem pilha. So for a small spherical particle, oh, that's not good. Voltou. Okay. So we have the momentum balance on the particle, which is essentially the equilibrium is mass time acceleration is equal to the resultant of all the forces. And there's a usually a lot used this Maxey relay form, which separates the different contributions on these forces on the particle. And some of them can be neglected depending on the situation. So usually the Bassett history force is not considered. The lift force also usually is only strong, very close to the walls. And but the other forces may be or not relevant. So the drag force is probably the largest, and when you have small particles with small Reynolds number, so you have this Stokes regime, the drag force is a linear force, which is related to the relative velocity between the flow and the particle. So U will be the velocity of the flow, and UP the velocity of the particle, and you have a force which is proportional to this difference, and and proportional to the viscosity and the radius of the particle. Another important force may be the gravity, which is related to the difference in mass of the particle and the mass of the flow, of the fluid flow that is displaced by the particle. And then there is the magnetic force, which is the one that we are going to include in this model. So I'll give a very fast overview of this. We are going to use a very simple model for the magnetic force. We have the we are going to consider a field which is a two-dimensional idealized magnetic field due to a line dipole. So you have a dipole which is placed close to the flow boundary, and that produces a dipole field. Right? So the dipole flow is, the dipole field is given by expression for the potential for the dipole field is given by the equation 4, and then from this we get the magnitude of the field, and the force that acts actually on the particle is proportional to the gradient of the magnitude of the magnetic field squared, given by this expression. So it's related to the particle volume and the particle susceptibility, magnetic susceptibility difference between the particle and the flow. So depending on the magnitude of the chi-p or chi-f, you can either have particles being attracted or repelled from the dipole. Okay, and here nu zero is the magnetic permeability. So it's not the viscosity. It's interesting to then define. Sorry, I think I jumped one or two. Let me see. No. Yeah, so we can define a magnetic drift velocity considering a balance between drag and magnetic force. So this will be the velocity that the particle will reach if you leave it in a stagnant fluid, with subject to a certain gradient of magnetic field. So, and this expression 13 gives the value of this drift velocity. Okay, of course, the drift velocity is a function of the distance from the dipole. So the closer you get to the dipole, the larger the velocity. And even though the magnetic field itself is solenoidal, the magnetic drift velocity is not solenoidal because it's not related to the gradient of the potential, but to the gradient of the magnitude square. So you actually get a strong divergence in the field close to the dipole. Actually, it goes to infinity if you don't put a limitation. So, we need to take care when we look at the transport that actually the divergence of the velocity of the particles due to the magnetic drift is not divergence free. It's very strongly non-divergence free. So we have, we'll look first at these forces, the drag force, the magnetic force, and the inertia. So considering first that the inertia is negligible, you have equilibrium, and then essentially the most important two forces will be the gravity and the magnetic force. So introducing the settling velocity and the magnetic drift velocity. Okay, so this is a very simple model. Okay, so basically you can say that the particle velocity is velocity of the flow plus the velocity due to the settling velocity, the gravity and buoyancy, and then the magnetic flow velocity. And well, those are dependent on, of course, various dimensional numbers, dimensionless numbers, and the main ones are the Mason number, which relates the representative magnetic drift velocity relation with the flow velocity. The flow number, which is related with the settling velocity, and the Stokes number, which is related with the inertia of the particle. So for very small Stokes number, the particle response is very fast. So essentially you consider to be in equilibrium. And for flows very large, the settling velocity will be small. So you can most of the time neglect gravity effects. And then you have the Mason number, which is strong when its effect is strong when the Mason number is small. Okay, so that's what you're going to look at. So to show how this works, we will look at this very simple setup. It's just a two-dimensional domain where a channel flow is flowing from left to right, and you have a laminar profile. So for the one-way coupling, you only have basically just a parabolic profile. And then you have a dipole close to the lower wall, which will introduce the magnetic field that will attract the particles. So if you look at just the streamlines for the Poiseuille flow, you only have basically parallel straight lines that the particles will follow from the inflow to the outflow. So nothing interesting here. And then if you look at the magnetic drift velocity only, you will get these radial trajectories pointing to the place where the dipole is placed. But when you combine, you get just a very simple algebraic thing that depending on the Mason number, you get all kinds of combinations, you know, from very small, very weak to a strong effect. So this is just a linear combination of the two velocities, and then you get all these different streamline, particle trajectories that so essentially vary only with the magnetic velocity. So from this, we can estimate how much capture of particles you get. So basically, the idea is to use the magnet to be able to capture the particles such that they don't leave the domain. So as the magnetic force is increased, you are actually removing more particles. So this can be seen by looking at the separatrix that divides the domain on showing the part that leaves the domain and the part of the particles that do not. So looking at the position where the separatrix meets the inflow, we have a coordinate ys, which is y of the separatrix, that can be employed to compute the removal recovery efficiency from using this information. So basically, if you integrate the mass flow from the bottom to the ys, you get the amount of particles that leave, and from so that's essentially the amount which is recovered. And integrating from 0 to h, you get the total amount. So the efficiency is basically just the ratio between the mass flux up to the separatrix divided by the total mass flux. So with this very simple model, actually, for this parabolic profile, we get a closed form calculations. So it's just a very simple algebra. But the interesting thing is how these things combine. So when you look at the efficiency as a function of the Mason number, here you need to only see that the scale is reversed. So this is large with Mason number is weak magnetic effect, and this is strong magnetic effect. So for very weak, you get no recovery. And as you increase, of course, the recovery goes up to 100%. And then from there on, you get perfect recovery, right? So this is basically a semi-analytic solution. Then using the same approach, we can also include the settling velocity, and then you have on top of the magnetic effect, you also have the gravity effect. So as you increase gravity, of course, you also increase the efficiency of removal or recovery. So this was using essentially a Lagrangian approach. So if you want to look at how diffusion may affect the recovery, we need to include a diffusion term. So we go to an Eulerian one-way approach. Okay, so instead of looking at the trajectories, we look at the field of concentration, right, of the particles. So this phi is a non-dimensional concentration of particles. And then you have this transport equation. So where you have a convective term and you have a diffusive term, and the Peclet number is the non-dimensional number that will control how much diffusion. You may say that since we are in a laminar flow and you have only particles that all have the same velocity in the vicinity, you essentially have no diffusion. So the diffusion only comes from random movements like Brownian movements, and they are really relevant only when you go to nanoscale particles. But still, we keep this just to show that, in fact, is not that relevant. So here we have a comparison of simulations where we have the semi-analytical solution, which is for Piclet going to infinity, and then for Piclet 10,000 and 1,000. So you see that the changes for very weak magnetic fields is somewhat visible, but for strong magnetic fields, you essentially get no difference in the recovery. So as a first approximation, you can either neglect the diffusion if you are interested in large efficiencies, right? It's because you'll be working with large magnetic fields. Now, we also can look at the actual acceleration. So looking at the Maxey-Riley equation, now with a little more detail, we have the same terms that we talked before. Here, this is a drag term, this is a gravity term, this is added mass. This is added mass. This is the resultant of the stresses of the fluid on the particle. And then you have magnetic, and you could have also lift, which is left over here. So we can apply this model to compute the acceleration of the particle and track the particle with the corrected velocity now, including inertia. So the equations, actually, you see that here is an implicit equation because the particle acceleration depends on the particle acceleration. So if you work out, then you get an expression where you can actually explicitly from the other terms compute the acceleration. But then, okay, now we can go and look at the two-way coupling. In this case, so the particle concentration is not so negligible, and then we want to actually see the effect of the particles on the flow. So in this case, we will need to solve actually the Navier-Stokes equations and the particle moment balance, and either the mixture momentum balance or the fluid separately, and the mass conservation. So we have the non-dimensional concentration is set up as a alpha 0 multiplied by phi. So phi is a non-dimensional variable that goes from 0 to 1, and alpha 0 is the non-dimensional volume fraction, right? So volume fraction is already non-dimensional. So of the particles, and alpha f is the volume fraction of the fluid. So the mixture mass conservation actually is the divergence of alpha f plus alpha p up. So you have already an effect of the fluid particle concentration on the conservation of mass. So this is the one that we need to include. Then we have an equation which is for the mixture. So you have the acceleration of the of the fluid and the acceleration of the particle. This is a non-dimensional form, right? So we have a pressure and have this stresses, viscous stresses, the gravity term, and additional terms like a magnetic and in this case would be the magnetic forces. Okay, so and this the acceleration it will be computed, of course, using this Eulerian approach. But here the acceleration of the fluid, the velocity, of course, is the velocity of the fluid, and the particle acceleration is the material derivative is taken using the particle velocity. Okay. So this is implemented using standard finite element methods, using a stabilizing technique, essentially streamwise upwind Petrov Galerkin. In a couple solution strategy, we use a grid-up library in Julia that allows to do this kind of coupled solutions in an easy way. And then here we have the effect of one example with two-way coupling. So this again is that blue line is the semi-analytical solution that they had before. This is the one-way coupling with the epic layout 1000, and this is the two-way coupling with the same Piclet number. So you see that essentially the effect becomes strong as you go to strong magnetic fields. And it actually changes quite a bit the value of the required magnetic strength to recover all the particles. So this is our examples of concentration fields on the steady state solution for various values of the Mason number. So here you have a small particle recovery. Here is larger, and this is complete particle recovery. So if you see, this is already a little bit different from what we had before. If you look at the streamlines, the particle trajectories for these two values, for instance, of magnetic intensity, you see that there is a deflection here, quite strong. And so this is already the effect of the two-way coupling. And what the two-way coupling causes, this is the flow velocity. You see that is actually forming a circulation on the upper wall that grows as you increase the magnetic field. So this is something that you only get with the two-way coupling. So other effect, which is interesting to look at, so we look at the before to the recovery efficiency, but there is another thing which is interesting, is to look at the hydraulic penalty, which is the head loss normalized by the head loss without magnetic field. So as you increase the magnetic field, what you see is that the head loss reduces. And surprisingly, it keeps reducing even after you removed all the particles. So in fact, from this point on, you get essentially a magnetic pump. So that's an interesting thing. So this is this very simple setup. You are already seeing a lot of very interesting results. Now we have this. Also can compute the distribution, the pattern of distribution of capture of the particles as you increase the Mason number, the magnetic strength. So in the beginning, you don't get much flux of particles. And then as you increase, then you reach a point where essentially you get all the recovery. And then the point of where the maximum location of deposition occurs starts to be displaced upstream. So this is the plot of the location of the maximum deposition. So it moves upstream as you increase the magnetic strength. So okay, these are the key findings. So the capture depends, of course, on the force balance. We see that the Lagrangian model is a very interesting model to show the effects, but is limited because we can't implement a diffusion model on it. And also it's hard to implement two-way coupling in the Lagrangian model. So the Eulerian model is more effective in the sense that it's more general, you can implement all effects, but also it's a lot more expensive. But we see that the two-way coupling is relevant even for quite dilute concentrations. You may get important effects from the two-way coupling. So of course, even though laminar flows are very important in these applications, many situations we use very small channels, so the flow can be considered laminar. Still, there are applications where you want to be able to have turbulent flows. So that's one thing that we will be moving on next. Also, maybe non-Newtonian applications, and of course, optimization and design with different geometries. Another thing that we also need to look at is that for now, since the solutions were very diluted, we didn't look at the interactions between the particles. So this will be the three-way coupling. And also for strong concentrations, we also have the effect of the particles on the magnetic field. So then you have let's say a fourth-way coupling, okay? So that was not included in this case. So even though what we show is quite simple, this framework is quite extensible because for the two-way finite element approach we use, we can employ to any general geometry and to do and explore the non-dimensional numbers ranges as required. So it's a quite useful framework to study magnetic particle recovery and other magnetic particle applications. So I think FINEP, which was the agency that gave financial support for the water quality research, and also CAPES, FAPERGIS, and PQ that give support to our program. And of course, thank again CMI for the opportunity to talk to you. Okay.
Thank you, Norberto, for this very interesting talk. I have one small question. You are solving that in coupled, right? So you assemble a huge system and do Newton. Is that right?
Yes.
With implicit method?
Yes.
Yeah.
It's in GridUp, you can choose what solver you're going to use inside the Newton. And yes, you use you can apply either direct solvers or like frontal solvers, or you can use iterative solvers with the preconditioner. So Julia has a very nice environment, and you can employ many libraries in a way, interconnected way. So you have a lot of freedom to choose the solver that you're going to use.
Very good. And does the time scales are different from the particle point of view and also from the fluid point of view, or more or less the same? I mean, they have different restrictions on time step if I want to go for explicit methods, for instance.
So in fact, what we solve is a steady state, and we set up basically it's implicit. So we use a time step which is based in the local CFL. So that also helps with the stability. So essentially we have a local CFL equal to 1, and with that we get the best upwinding effect. So we get a stable and a more accurate result. So in a way, it mimics a semi-Lagrangian approach.
Oh, okay.
So we, at each step, we move one cell.
Okay, questions? Sean?
Interesting talk, Norberto. If my memory serves me rightly, if you have turbulence, you need to include the Bassett history term. I did a lot of work on this about 50 years ago, which I'll maybe talk to you about. The other question was the Mason number. I haven't come across that before. I noticed you used MA and MN.
Sorry for that.
But is it I'm probably wrong here, but is it the average fluid particle velocity to the average fluid velocity?
I saw it defined in different ways. So one way is basically based on force. So it will be viscous force to magnetic force. So on the contrary, magnetic force. No, that's it. That's it. Viscous force over magnet. So when the Mason number is large, then you have weak magnetic force.
Okay.
And but then what I'm using here is, since I use for the non-dimensionalization, I use the average flow velocity of the channel. So it's what I'm using is the channel velocity versus the magnetic drift velocity. Okay.
Okay. Yeah.
It's not the conventional Mason number.
Thank you.
Anyone else? Santiago?
But in fact, I'm not doing the turbulence right now. So yes, we can include more terms. You didn't put even the lift force, but I mean, I think the strongest effects were the Mason, and Freud, if in case it's relevant in your case, may help, and then the two-way coupling is quite interesting. So if you put a more fidelity in the acceleration of the particles, of course, we will have effect, of course. So you include the Bassett number, the Bassett effect, Bassett term, the lift force. So it will change, but I think the magnetic force is so strong that essentially dictates how you're going to capture or not the particles.
Thank you for the talk. I have two questions. Maybe I missed it during the presentation, but what is the concentration of the particles, or alpha, I think?
Yes. Alpha 0 is the volume fraction.
Mm-hmm.
So we are working with 2.5 times 10 to the minus 2 at most. Okay, so it's 0.025 at most.
Okay. So
That's the case where I show the strong effect. For 1 times to the minus 3, then the two-way coupling is weaker, much weaker. So, but 2.5 times minus 2 is still quite dilute, and you see quite a strong effect.
Yes, I know. It's a very good range for that model. And what is the Reynolds number?
Oh, for these runs, the Reynolds number was just 10. So it's quite laminar. But yes, we can, it's that we have so many parameters that we run, you know. This is already for these curves here, I have something like 100 runs just for Reynolds 10, you know. So, because we have a lot of parameters. So, of course, we can look at higher Reynolds numbers. Not for the Lagrangian, it doesn't make any difference because it's one-way coupling. So the Reynolds number of the base flow doesn't make any difference on the results.
Okay, thank you.
Well, let's thank Norberto again. Thank you, Norberto.
Thank you.
Santiago. I will let Roberto introduce the next speaker.
Well, apparently the Argentinian guys are in charge of me, so I will introduce Santiago Marquez. He's a leading expert in the area of CFD. He knows very well OpenFOAM or all these platforms, methods based on finite volumes. He's an independent researcher from CONICET, which is like the CNPq of Argentina. And he's a professor at the Universidad Tecnológica Nacional. And he is a civil engineer, and he also works in CIMEC, right? This is in Santa Fe. It's a center, a very well-known center of numerical methods in Argentina. Well, he will present us his recent work on hydrodynamic lubrication. So I let Santiago with you.
Thank you, Roberto. I have to connect to the internet to use the presentation, so let me take some minutes. Vamos ver o que acontece. Não sabia que tinha que conectar. Não vou descarregar o PDF e vamos ver o PDF diretamente. Tem uma de aqui? Tem uma conexão de aqui? Esse seria audiovisual, hein? Qual é aqui? Esse CTI? Qual é aquele? Ele investe. Aí o login assim com esse daqui. Esse aqui? Ah. Mas é na. Como é que tá na. Em underline guest. Aí. Esse aqui? Yes.
While we are waiting, I just remind you to cast your votes up to the lunchtime, all right? So we can do the final scoring and for the best poster award, all right?
Aqui. Agora posso. Agora sim.
All right. Good, good. Floor is yours.
Okay, ready. Well, I'm very grateful to be here for the support I received to arrive to Sao Carlos and to share this moment with Professor José Alberto Cuminato in his 70th birthday. Yesterday, I learned that the CMI was born in 2013. I was here at that time, but I thought that the CMI was here for many years. But when I checked the website, I went to the first report that Professor Cuminato presented, and then I found some interesting name there in the computational free dynamics team from ICMC. I found myself and other professors who are here today, obviously Professor Cuminato too, and it was really interesting to know that I was a part of this starting center at that time, and it's really, really good to be here and see the fruits of that creation at that year. Okay, So let's go with the content. I'm talking about general hydrodynamic general bearings, particularly the couple effects on of the temperature and the surface textures on the hydrodynamic bearings. So the idea is to present the state of the problem, to talk about the theoretical model and numerical method, then the software implementation. Part of this implementation was done in OpenFOAM. The results and discussion, and finally the conclusion and some remarks. Well, the statement of the problem is the following. In texture journal bearings is very common or well known that you need to use conservative models and to take into account the thermal effects. But if you check the literature, you will see that these two topics are discussed independently. Maybe not so. You cannot find much literature with both effects together, and they are very important, particularly the thermal effects. But you cannot forget the conservative model. So we are using a conservative model with thermal effect included to show the differences you have if you don't consider both effects together. So, well, a hydrodynamic journal bearing is a machine part that supports a shaft using the pressure fields which appears when you rotate the shafts into the journal. The journal has, or the shaft has an eccentricity, and this poses the pressure field. You have a conversion and a diversion part between the shaft and the journal, and in the diversion part you have cavitation, or you can have cavitation, different kind of cavitation. And this topic of the cavitation is also not well discussed in the literature. Many researchers work with cavitation, but different kind of cavitation, and the type of cavitation is not well described usually in the literature. So you can have smooth surface hydrodynamic bearings, but you can also texture the surfaces, the journal surface as well as the shaft surface. Texturing the shaft surface is not so common, but you can find some experiences in the literature. So some remarks here. What is surface texturing? Well, they are intentional cavities in the shaft of the journal versus the roughness. Roughness is just the finishing of the surfaces in the fabrication process. It is generally accepted that textures improve or can improve lubricant film performance. How to put the duct textures, the depth, the position, and some characteristics is not so easy to find. Or you can obtain increasing load current capacity, reduce friction. You can retain wear debris inside the texture. You can enhance the lubricant film stiffness, and you can use the textures as cavitation concentrators. I mean, you can concentrate the cavitation inside the textures and control its effects. It's well known that you need to use mass conservation mass conservation model to model cavitation. Roberto Ausas has some works on that, and we use that works as a guidance. Thermal effects are often overlooked or not studied along mass conservation models. I mean, both effects together. But both topics must be taken into account to avoid misleading results in texture's hydrodynamic general building design. So the theoretical model, we presented our theoretical model and the numerical method in that paper. I think I talked something of that in the other workshop in 2024. But we are recalling the model to set up the ideas before the application. So we are working with a mixture model. So we have all mixture dynamics. We have mixture viscosity. It has a linear average, just a linear average. You can also use the harmonic average to compute the mixture viscosity, but in our tests, the linear average gives the correct results against the experimental results. We have a pressure equation. We have pressure equation for the mixture and a liquid transport equation for the, obviously for the liquid fraction. Alpha gives you the fraction for the oil. And you have a phase change term, which accounts for the cavitation. The thermal effects in this case are taken into account in a 0D model. We are working in a 2D model for the thermal effects, but for these cases, 0D model is enough for our purposes. We have a model for the temperature increasing and a model for the viscosity variation. This is the below the water model. The main part of the model is this second order conservative algorithm. Checking the order of the conversion order for the numerical method is not so common in the tribology literature, but it's important. We have a 2.D FBM discretization for the pressure equation. I mean, 2.D is two-dimensional, but with integration in the height. And we have two implementations. One in the scientific computing platform for Octave, which is an interpreted language, and a implementation in OpenFOAM with the finite area method. I will explain what is finite area method. So we have three cavitation models for the source term. We have a model for the vaporous cavitation, which is the classic one. So at some point, the pressure goes down and just the oil transforms in vapor of the oil. You have the pseudo cavitation, which is just the change in volume of the air bubbles you have inside the oil. And finally, you have the gaseous cavitation, which is an extension of the Henry's law. This model captures the process to, we don't have the word for this particular process. We check the name with chemists, but they don't have the word too. The idea here is when you like in the soda cans, when you increase the pressure, you can absorb or dilute more gases inside the liquid. When the pressure goes down, these gases go away from the liquid. But for that, you have the Henry's law. But the Henry's law is just an equilibrium law. It's a law for the equilibrium, or for the concentration of the gases in the equilibrium. But in this case, we need the dynamics of the absorption of gases. So we take a a gaseous model or extension of the Henry's law from the literature, and we adapted to gaseous cavitation in hydrodynamic bearings. So we have the three models, and we set the model according to the experimental data. We also have a TBD method to correctly capture the advection processes, and a temporal strand splitting to have second order conversions in time. Well, we have an algorithm, and we solved the equation in sequence, but we have internal loops in order to retain the second order conversions. And finally, we obtained it. We obtained second order conversions in position, liquid fraction, and pressure, which makes the model really reliable. We check that with some cases from the literature. Basically, we put the shaft in the center of the journal, and we follow it until the equilibrium position. And we check the trajectory, the pressure, and the liquid fraction. Well, the software implementation, we have, as I said, we have two implementations. One in the Octave, which is a platform for rapid prototyping. We can run some industrial cases in that platform, but without textures or without small textures. And then we have another one in OpenFOAM for high demand simulation for smart textures. So what is finite area method? Well, why not finite volume method in 2D? Okay, finite area method is a name inside OpenFOAM. The idea here is, in OpenFOAM, all the meshes are 3D. So when you want to run finite volume method in 2D, what you have to do is create a 3D mesh with constant height, and then you run some preprocessing tools to transform that 3D mesh in a kind of 2D mesh. I mean, you transform the interest from the volumes and faces to the surfaces and edges. Finally, you have another field that is the height, h. And the other thing is, even when this technique is inside OpenFOAM, it's not widely used and not undocumented. It's okay, it works very, very good, but no, you don't have many solvers using that technique. So we had a time over there checking the code, etc., and learn from the code how to use this technique. Well, the finite area method, we discuss the equation by the finite area method, finite volume method. This code is named DINCAFlow. I mean, DINCAFlow is the OpenFOAM version, and DINCAV is the version in Octave. We use DINCAFlow with cases up to 6 million cells running in parallel, but you can also run bigger cases if you want. The thing here is that you need to run in time, so you can go up in the number of cells, but the runnings are slow, or you need to run a lot of time steps. Well, we have results and discussions. The results are presented in this paper in the surface topography, metrology, and properties. We were working with Professor Francisco Profito. He's from the USP, Escola de Ingeniería. So he had the experiments, and we contacted him directly to know more about the experiments and the details of the experiments, because, as you know, sometimes some details are not present in the papers. So he finally ended as one of the co-authors. Well, we first checked the pressure field. We validated the pressure field. We used a case from Manser and collaborators, and we checked the Reynolds solver with a full CFD solver solving the Navier-Stokes equations. Then basically we have two cases, one with smooth surfaces and one with textured surfaces. In the smooth surfaces, our results were almost the same of Manser, but in the case of the textured surface, Manser has smooth results. You don't have many perturbations in the pressure on the pressure field. So in order to resolve this problem, we ran the case with a full Navier-Stokes solver, and the Navier-Stokes solver, as is shown here, is showing this sawtooth profile. So our model was checked against the CFD model, and this is the correct behavior. The Reynolds equation with textures is not always giving you the correct results. When the textures are deeper, the Reynolds model fails. But for the usual texture you use in the industry, the results are correct. We are checking these ideas now with other people, but in this setting, the results are correct. Okay, what about the friction and thermal model validation? Here we use the results from Profito. Basically, he performed some experiments with textured surface. Basically, they are kind of spheres or hemispheres. These hemispheres have a diameter of 70 micrometers. So the scales of the textures against the scale of the hydrodynamic bearing was very different. So we have to use a really fine mesh in order to secure maybe 10 elements inside each texture. So our results, we are checking here the temperature rise and the coefficient of friction, which is a measure of the friction weighted with the low current capacity. So we are okay with the temperature rise. The triangles are the experimental results, and we are fitting the experimental results with a very good trend. Then for coefficient of friction, you have two cases. One is smooth and the other is textured. Here is these are the results for the experimental smooth case. And we are following the trends very good. And the other one is the texture case. And we have divergence here. Our results underestimates the coefficient of friction. But we attribute this to maybe to when you have small speed rotating speeds, the surfaces can enter in contact. So when you have metal to metal contact, the temperature rise is greater than just the friction of the oil. So in order to check what happens with the real textures, we checked a very simple texture, which is this triangle. It's a very big texture, as you can see. This is the width of the general bearing, and this is the triangle. This particular shape is a very known texture shape. You obtain kind of a pumping effect because the way the form, the shape of the texture. Professor Nicoletti here in Sao Carlos, he experimented with this kind of, like this kind of texture. We worked with him for the first paper. And as I say, these are very known texture shape. So what are these results? We performed here to test first with a relative eccentricity of 0.3, and the other one was 0.6. The relative eccentricity gives you a measure of how near is the shaft to the journal. When you approach 1, the shaft is touching the journal. So as you can see here, the temperature rise is very similar in the smooth and texture case. This is not a real problem. But in this figure, you can see that the texture and smooth cases follow the same trend, but the results with the isothermal and the thermal model are really different. So if you don't take into account the thermal effects, you are really missing the point with the load carrying capacity of the journal bearing. Regarding the friction torque, it's the same. The texture case and the smooth case follow the same trend. The results are very, very similar. But the differences between the case with the isothermal and thermal models are huge. Okay, and then this is a very important conclusion here. Then this is for 0.3, and for 0.6 is the same. Maybe you have little differences between the case of the smooth journal and the texture one. So the first conclusion is this texture is not adding much load carrying capacity. It's not a very good texture. But as you can see, it's a really simple case. Usually you have smaller textures, and they are distributed in very specific places. So we can continue. We have marked this case, which is 2000 RPM. And this is the case, also with 2000 RPM. And then if we check now what happens with relative eccentricity, I mean, you move from 0.3 to 0.8. You can see the previous case here. The trends are similar, but, or if you see here, when you go up in the relative eccentricity, the friction torque is almost the same between the smooth and the texture case, but you continue to have differences between the isothermal and thermal cases. But the main conclusions are from this picture, because you can compute some differences in percentage in leakage and oil leakage, load carrying capacity, and friction torque. And if you see here, if you follow the isothermal curve, which is the blue one, for 2000 RPM, at this point you are having a little increase in the load carrying capacity because they use the textures. But if you see the case with the thermal model, the reality is just the opposite. So maybe you are judging this texture as low carrying capacity improving texture, but the reality is just the opposite. And this case is a very simple case with a very simple texture. But the important thing here is you have to be very careful with the models you use and the conclusion you obtain. And this is basically the main conclusion of this work: the importance of the thermal model and the importance of use this thermal and conservative model when you are checking the load carrying capacity in textures. Well, you have the same thing, and even more clear when you check the friction torque. You can see here that the difference is almost 3 or 5%, which is pretty much in a journal beating. So some conclusions. We have very good agreement between both techniques. I mean, using the Reynolds-Riley-Plesset equation and the CFD. And this allows us to use this kind of 2.5D solvers instead of CFD for hydrodynamic general bearings. We validate our code with experimental data for temperature rise and friction, which is a gold standard, obviously, but not always possible. In this case, particularly, it was really difficult to obtain experimental results. And we obtained the experimental result for a paper, but reading the paper wasn't enough to understand what was happening there. So we had to contact the authors. The use of textures is detrimental in high eccentricities in cases where isothermal solvers report benefits for this particular case. And for thermal effects, conservative solvers considering thermal effects are mandatory, and the exceptions should be properly justified. For example, you have some cases when the experiments are performed sustaining the temperature with a liquid bath, for example. Okay, the credits, Connie said, Universidad Tecnológica Nacional, where I am a professor, Escola Politécnica at USB, CMI, and ICMC. So thank you.
Questions? Anyone? Michael?
Thank you very much. Can I just ask, so the geometry that you're solving in, so you have like an inlet and an outlet here between so you have the bigger circle and the surface below, and do you have to specify
here?
Yeah,
there.
right, yes, on this one. Okay. Oh, so so you flatten out the.
Yes, I flatten out the real geometry because of the hypothesis of the Reynolds equation.
Oh, okay. Yeah.
You can do that because the height of the oil film is really negligible against the length of the oil.
Okay, and then in flattened out geometry, what is the aspect ratio of that flattened out geometry?
For example, you have maybe 5 centimeters all the way around, and you have 10 micrometers in the oil film thickness. Order like this.
Yes. Okay.
10 micrometer, 20 or something.
Okay, and then the actual the textures, they are compared to the 10 micrometers. Are they also 10 micrometers, or are they even smaller than that?
Or the 10 micrometers.
Okay.
Yes. If you go down like 1 micrometer, maybe you are in the order of the roughness. So if you are using laser or something, maybe you need to work with 5, 10, 20 micrometers.
Okay, thank you.
More questions? So in the 3D simulations, you included in the simulations that you did with the OpenFOAM, right? So you included the textures also. And how do you do that exactly?
In this case, here, in the 3D, in the full and the full Navier-Stokes equations, when we use the full Navier-Stokes equation, we run a really 3D full Navier-Stokes solution.
Oh, with the geometry of the texture.
And this is the actual geometry.
Oh.
This is not unrolled; it's rolled.
Yeah. All right.
But the other OpenFOAM simulation, the one we use for this, is unrolled, and the height is represented by another field, the field H, which is the height.
Yeah.
So you enter this parameter in the Reynolds equation.
Yeah. All right. So in the other case, the mesh should be very fine on this to capture that.
In the full 3D Navier-Stokes solution, yes. Maybe you have 30 elements in the height, and you need to maintain a very good aspect ratio. So you have a lot of elements.
So your CFL number is quite tight over there, right? Also.
It is not so a problem because you are in a very low Reynolds, Reynolds case.
Yeah.
So
sure.
The velocities are not so high.
Okay. More questions? All right, so we have lunch, and we're free to go, and we will resume here